Okay, we're going to go over a Fourier analysis practice final exam, 10 problems. Um, we'll have the setups and explanations for a majority of the problems. The arithmetic, algebra, and some of the integration I won't be putting in between the steps. You could fill in the blanks, but hopefully this helps if you're preparing for final exam in Fourier analysis, or you just want to review uh, Fourier in general. Okay, so let's jump right into it. So number one here, we let f of x equals x squared, defined on the interval negative pi to pi, extended periodically. So part A, compute the Fourier series of f, and part B, use your result to evaluate the series n equals 1 to infinity 1 over n squared. So this, again, I'm just going to say this before, this basically prerequisites Calc 1, Calc 2, Calc 3 differential equations, and fundamental working knowledge of series before jumping into Fourier analysis. But a lot of you already know that. Okay, so let's get right into it. So this Fourier series, since x squared is even, the cosine terms will appear, and we have f of x equals a naught over 2 plus that sum, n equals 1 to infinity, a sub n cosine of nx. The cosine terms even, sine terms odd. We're going to compute a naught. Okay, so if we do all that computation for a naught, finding the coefficient there, a naught here, a naught over 2, after we do all the computation, is pi squared over 3. Okay, so now if you want to call that a sub 0, I'll call it a sub 0, or a naught, whichever. I'll use the terms interchangeably. And then if we want to compute a sub n here is 2 over pi, integral 0 to pi, x squared cosine nx, okay, dx. So think about this, even functions are associated with the cosine. Now, just to skip over some of the work we need to do to get here, Calc 2, integration by parts. What we're going to do is we're going to apply integration by parts 2 times for this, and here's what we get, right? We're going to be able to take a sub n 4 times negative 1 to the n over n squared, and we're going to be able to find the final Fourier series of this. So x squared is going to equal pi squared over 3 plus the summation n starting from 1 to infinity, 4 times negative 1 to the n over n squared, cosine of nx. Okay, so the computation portion involving the algebra, the trigonometry, and the integration by parts, that was left out. You could try that. So this is a bit of a longer problem as far as computation wise to arrive at this final Fourier series, but you could do that and just see if you got this for your x squared. Okay, second part of the problem, we want to use our result to evaluate the series. N equals 1 to infinity 1 over n squared, so we set x equal to 0 and we solve. X equals to 0 and we solve. So when we do this, we're going to wind up with something familiar here. We're going to get negative 1 to the n over n squared. That's going to equal negative pi over 12. That's when we solve, right? And if we use identity, 1 over n squared here, n equals 1 to infinity, we're going to wind up with just pi squared over 6. So to evaluate this series, this comes out to pi squared over 6 using what we know from the final Fourier series and just solving, and from identity. Okay, so that takes care of number 1. Again, I'm going to go through these quickly, assuming you have a working knowledge of Calc 1, 2, 3 differential equations, and you had a full Fourier course. maybe at signal processing too. But I'm going to go kind of quickly and omit some of the, again, some of the work in between. Okay, so that was number one. Let's move along now to number two. Okay, so number two, let's see what we have here. So number two, we let f of x equals x on the interval 0 to pi. Okay, so there's the interval 0 to pi. Part A we'll do first, construct the odd extension to negative pi to pi and compute its Fourier series. So odd extension, think sine, right? Sine series. And the odd extension provides f of x n equals 1 to infinity b sub n sine of nx. We want to solve for b sub n. We get 2 over pi. And now this integral 0 to pi x sine of nx dx. Okay? So, go back and review if you forgot where that comes from, but that's just we have f of x times sine of nx dx, and then the b of n. Okay? This b of n becomes this. Okay? So do the work, see if you arrive at that. Now again, if we do the work here, I'm just going to put what b sub n becomes. After you integrate this by parts, think calc 2, b sub n equals 2 times negative 1 to the n plus 1 over n. So we're going to get for the final sine series, letter A, x is equal to n equals 1 to infinity 2 times negative 1 to the n plus 1 over n times the sine of nx. So A, that's what you get. There are parts omitted involving computation, but these are the answers you arrive at. Okay. Now for letter B, we want to construct an even extension and compute its cosine series. So again, what we have here for even extension is going to be a sub n equals 2 over pi, 0 to pi, x cosine now, nx dx. And after going through the computation, we're going to arrive at a sub n equals 2 over pi times negative 1 to the n minus 1 over n squared. Okay? So, that's our a sub n. Okay? We're good with that. And now moving forward, compare the convergence at x equals 0 and explain any differences for letter C. The convergence at x equals 0, odd extension, function is continuous at 0 and converges to 0. Even extension, what we do here, there's a jump at 0 and converges to the midpoint. So 0 plus 0, take the average, over 2 equals 0. However, we could say the behavior differs due to symmetry and the boundary behavior. Okay, so just going to go at a quick pace, providing the steps in between, and you could check your answers as you go along. Remember, this is something that's, you could say, is interactive, whatnot. If you want to pause the video and try the problems without looking at the answers, that's fine. Do whatever you see is best for you. All right, so that takes care of 1. That takes care of 2. 20% of the way there. Let's move along to number 3. Okay, so number 3, we have let f of x be the 2 pi periodic function defined by this piecewise. You have f of x as 1, negative 1, and here are our domains for each, respectively. Compute the Fourier series here. So what can we say about this function? Well, the function, we want to find out if it's even or odd. It is odd. Okay? So we choose a sine series. So we have b sub n is 2 over pi. We're integrating from 0 to pi. Negative 1 sine of nx dx. Okay, so here b sub n equals negative 2 over pi times 1 minus negative 1 to the n over n. And in this situation, let's look at only odd n. B sub n equals negative 4 over pi n. That's for your odd n. So if you go through the steps, you'll arrive at that for B sub n. Remember, some steps are omitted just to speed things up. A lot of the computation stuff and stuff that's assumed that you know as far as relationships with the series. So the final series here is going to be f of x equals negative 4 over pi, and then we could write this out of what this would look like here on the right hand side, the quantity sine of x, and then plus 1/3 sine 3x plus 1/5 sine 5x. Next term would be 1/7 sine 7x, then 1/9 plus 1/9 sine 9x, and so on and so on and so forth. So that's what we get for our final series for letter A. For letter B, we want to determine the value to which the series converges at x equals 0. So a value at x equals 0, okay? Think about this function. We have a jump from 1 to negative 1. Find the midpoint. Take the average of those outputs there. 1 plus negative 1 is 0 divided by 2 equals 0. So determine the value to which the series converges at x equals 0, and we get that 0. Okay. Now letter C, explain the Gibbs phenomenon in this context. So in this situation, Gibbs phenomenon, so approaching or near 0, the partial sums, what they're going to do is they're going to overshoot the jump and they're going to start oscillating. Okay? This overshoot does not vanish. It's important to mention that. Does not vanish even as n approaches infinity. So that's our Gibbs phenomenon. So that's 3, A, B, and C, and we're moving at a quick pace through this. You could use, again, multiple ways of doing this. You could go and do these problems one by one. You could fast forward ahead and just copy the problems down and do try the whole practice exam first, and then come back to check the answers, whichever you prefer. Okay, so this one we could do, we could explain through quickly. And again, the computation, I leave it up to you with some of the intermediate steps. If we want to compute now the Fourier transform of f of w, think of angular frequency, negative infinity to infinity f of x e to the negative I w x dx. So for f of x on this piecewise, e to the negative ax, define where x is greater than or equal to 0, and the output 0 where x is less than 0, and our a value is going to be positive. So if we go through the computation here, okay, we're going to get f of w 0 to infinity, and then we're going to have this product here, e to the negative ax, e to the negative I wx, integrating that with respect to x. So this is a single variable integration. And integrating with respect to x, 0 to infinity, we get e to the negative a plus I wx dx. And after we employ this Fourier transform, we're going to get 1 over a plus iw, where a is greater than 0. And that's after doing all of the work. So this one, you could do the intermediate steps just to check. I encourage you to do the intermediate steps to check, especially if you're preparing for an exam. And this is where we wind up at for the conclusion of the Fourier transform for that problem. Okay, so that takes care of number 4. Again, we're going through these rather rapidly. Okay, so that's 4. And let's take a look at number 5. Okay, number 5. Compute the inverse Fourier transform of f of w equals 1 over w squared plus a squared. And then we're going to use the convolution theorem to compute this. You could say this f asterisk f of x. Think about what that means in terms of convolution theorem, bringing those functions together. where f of x equals e to the negative a times important absolute value of x, not just x, absolute value of x. You've probably seen that before. So, inverse Fourier transform portion, f of w equals 1 over w squared plus a squared. And this is known as a known result. If you employ knowledge of that, Fourier transform, inverse Fourier transform, f of x equals pi over a e to the negative a times absolute value of x. Okay, so those tables come in handy back and forth with inverse and Fourier transform both. Now, by convolution theorem, what we could say is if f of x equals this function, e to the negative a times absolute value of x, okay, then what we can do here, we have the bringing together of f and f of x, f asterisk f of x, that's going to equal the integral from negative infinity to infinity times e to the negative a, absolute value of t, that's multiplied by e to the negative a, absolute value of x minus t dt. Okay, so you need to know how the convolution theorem works, how you could write this out. And there's your result in the end, f asterisk of f of x, f asterisk f of x in this situation equals 1 over a times e to the negative a to the absolute value of x times the quantity 1 plus a absolute value of x. So that is our result. After we do all of this, left out the integration, left that up to you, and see how we arrive at that. Okay, so moving along, that's number 5. And now we go to, I think this might be number 6, might be the longest problem in the exam, number 6, in the practice exam. Okay, so here we have the heat equation application. So we have partial differential equations, PDEs here. So solve the heat equation. We have U sub T equals UXX 0 to pi. T is greater than 0. Boundary conditions are given up here. Initial condition given here. Okay, so you've probably seen this done, especially some of you may have taken or been interested in partial differential equations, the heated ring, Fourier experiment, where the heat equation comes from. It's interesting. It's interesting stuff. So first step here with the heat equation, we want to separate the variables. So what we're going to do is we're going to assume U of x t equals capital X of x t t. So we're dealing with temperature and we're dealing with space. Okay? Now substitute into the partial differential equation. Okay? Substitute into what we're given. Now we're going to have x times t prime equals x double prime of t. And if we set up a proportion here, bring the t's on one side, the x's on the other. You get t prime over t equals x double prime over x. Okay, so we're relating these two things here. Okay, and equal to negative lambda. In this situation, this is going to be equal to negative lambda. Okay, so heat equation, we're thinking of time, we're thinking of space, we're thinking of temperature. Okay, so now second step, and this requires knowledge of differential equations. It looks like we have a second order differential equation here. If we set this up as x double prime plus lambda x equals 0, x of 0 equals 0, x of pi equals 0. We want to get the eigenvalues here. So when we do all of that work solving that, eventually we get these eigenvalues, lambda sub n equals n squared, x sub n equals sine of nx. Okay, now we wind up with our third step. From all of this, we want to generate a time solution. So capital T sub n equals e to the negative n squared t. That'll be our time solution. Now, I'm going through this quickly. Hopefully I'm not misspeaking, okay, because we're dealing with, technically, we have time, temperature, and space involved here in some way, shape, and form. So here's our time solution. Now, just go and check your work if you're doing this. Just want to make sure you arrive at these and that this makes sense, how all of this became that. Step 4, here's the general solution. Your general solution in this situation, we're going to take what we got in steps 2 and 3, general solutions. U of xt equals n equals 1 to infinity b sub n sine, okay, sine of nx e to the negative n squared t. Okay. Now, what we want to do here, and this is where we're going to have to break this up, we want to find the coefficients in step 5. So b sub n is 2 over pi integrated from 0 to pi x times the quantity pi minus x sine of nx dx. So if we expand this, we get pi x minus x squared. And what we're going to do here is we're going to divide the integral into 2 components. Okay, so we're going to divide the integral into 2 components. In this part of the work, I'll show. So the second page, we'll take care of it. So let's see here. Whoops. Do this part first. Okay, so we get b sub n is 2 over pi. Separate this, pi 0 to pi x sine of nx dx minus 0 to pi x squared sine of nx dx. So we're going to use standard integrals here. First component, 0 to pi x sine of nx dx. Okay, that's going to come out to negative pi times the quantity negative 1 to the n over n. That's what that's going to come out to. Second component here, 0 to pi x squared sine nx dx. This is a negative pi squared. I wrote this up here, negative pi squared. So that's a negative pi squared times negative 1 to the n over n plus 2 times negative 1 to the n over n cubed minus 2 over n cubed. So what we're going to do here is we're going to place these integrals together from what we had on the previous page, 0 to pi x times quantity pi minus x sine of nx dx. Okay, that is going to equal this. Okay, putting the integrals together. Okay, putting these together, we're going to get 2 times the quantity 1 minus negative 1 to the n over n cubed. So that computation wasn't shown. Just do the computation and you arrive at this portion when you blend them together, put them together rather. Now b sub n equals 2 over pi times this. B sub n equals 2 over pi times this piece. So it's just going to be 4 times the quantity 1 minus negative 1 to the n over pi n cubed, right? So just as a side note here, we'll go over this at the end here. Our final answer is u of x of t, n equals 1 to infinity, 8 over pi n cubed sine nx e to the negative n squared t. This is a sine So where n is odd. This would be the final answer. And just right over here, for simplifying the coefficients, if n is even, then 1 minus negative 1 to the n, okay? So this 1 minus negative 1 to the n, that would equal 0, and b sub n would equal 0, okay? That would be gone, right? B sub n would be gone. And if n is odd, 1 minus negative 1 to the n equals 2. So if that's the case, if this becomes 2, right? That's where we get that 8, right? So 4 times 2 over that pi n cubed. So that's that b sub n, okay? Just wanted to show that just in case. So that was the longest one. Well, one of the longest ones. It depends on how you view it. That's number 6. So we're 60% of the way through. All right. So let's move along now. We have number 7. So number 7, we have let f of x equal x on interval negative pi to pi. Part A, compute its Fourier series. If we're going to compute the Fourier series here, f of x on x, negative pi to pi, this is odd. Since x is odd, we do a sine series. So f of x is f of x is n equals 1 to infinity, b sub n sine of nx. B sub n equals 2 over pi, 0 to pi, x sine of nx dx. So this looks kind of familiar. And that's going to come out to, when we do the work, 2 times negative 1 to the n plus 1 over n. Or you might have remembered that. Okay? So we could say our x value is going to be n equals 1 to infinity, that's summation, of this, b sub n, right? This is b sub n times sine of nx. Okay, so that would be the computation of the Fourier series in relation to the function and the interval given. And now for part B, they want us to use Parseval's identity to evaluate n equals 1 to infinity 1 over n squared. So what we do here, you need some knowledge of course, Parseval's identity. Parseval, in this situation, 1 over pi, negative pi to pi. This becomes x squared dx equals this. N equals 1 summation to infinity of b sub n squared. So you're relating the function, okay, to this, the integral of this to this series, right? So here we have the left side. Okay, if we do this, we get 2 over pi, 0 to pi, x squared dx equals 2 over pi times x cubed over 3, 2 pi over 3. The right side, 4 over n squared. Okay, and we set 2 pi squared over 3 equal to 4 summation of 1 over n squared. And the final answer, when we just do the computation, is going to be pi squared over 6. Pi squared over 6. Okay, so there we go with that. Moving forward, that's number 6. Number 8, C. So for number 8, let f of x have Fourier transform f of w. Show that the Fourier of f prime of x equals I w f of w. And then part B, use this to compute the Fourier transform of f of x equals negative a times the absolute value of x. So, okay, so we want to show that this equals this. And here's the proof. F Fourier of f prime of x, that's going to be set equal to negative infinity to positive infinity of f prime of x e to the negative I w x dx. Okay, so what we want to do is set this equal to that, and now we're going to take the integration by parts. I skipped some steps, just integration by parts. We'll let u equal e to the negative I w x, dv is f prime of x dx, uv minus the integral of v du, and now we get this. Okay, we're going to wind up with f of x quantity times e to the negative I w x, evaluated from negative infinity to infinity, plus I w f of x e to the negative I w x dx. Okay, boundary term here is 0. Now, if you were to go and do all of that, you're going to arrive at I w f of w. So indeed, if we go back, if this, okay, is equal to this, and then we evaluate this, we have shown that this becomes what we were looking for. The original equal to I w f of w. And again, I omitted some steps with the computation and whatnot. So just go and try it on your own. You're encouraged to do so. And then for part B, we're computing that Fourier transform. So we're going to use the result. And now we do f of x of f of x, right? Fourier of that transform equals I, derivative with respect to w, dw, f of w. Now it's known from tables f of capital F transform of e to the negative a absolute value times absolute value of x equals 2a over a squared plus w squared. So what we can do here, if we have f times f of Fourier transform of x times e to the negative a to the times absolute value of x, these are very closely related. This is going to be I times the derivative with respect to w, the derivative there, times 2a over a squared plus w squared. Okay, so we're only worried about w there. We're only worried about the w there. So differentiate, you get I times negative 4aw over a squared plus w squared squared. So this Fourier transformation of xe raised to the negative a times the absolute value of x is just going to be this, negative 4iaw over the quantity a squared plus w squared squared. Okay. So that takes care of number 8. So moving along to number 9. So for number 9, Dirac. Okay, so pardon me with my delta. I apologize, I do not draw delta well, so please bear with me. So for 9a, compute the Fourier transform of the Dirac delta function, delta of x minus a. And for part B, we want to solve this differential equation here, u double prime minus u equals delta of x using Fourier transformations. Okay, the Dirac delta. So, okay, so for letter A, the Fourier transformation of the Dirac delta function, okay, if we take the integral of delta x minus a e to the negative I w x dx, remember what the delta function is, what it yields. We're just going to get e to the I w a. That's you can do that quickly if you remember what delta function comes down to an integral form. All right. Part B, solve. U double prime minus U equals this delta. Okay. What we're going to do here is we're going to take the Fourier transform. We're going to get negative W squared minus 1 times U of W. That equals 1. We're going to isolate U of W. We're going to get 1 over, isolate U of W. We're going to get 1 over negative W squared plus 1. So what we want to do here is we want to find the inverse transform. Okay, that's known. Inverse Fourier transform of 1 over W squared plus 1. And that's going to come out to 1/2 e to the negative absolute value of x. So what we could say here is u of x equals negative 1/2 e to the negative absolute value of x. So that is our answer, and that would solve that differential equation with the delta function. Okay, I skipped some steps with computation and whatnot, but you feel free to try. So that's it for number 9. Okay, and now number 10 is going to be stuff from textbooks and notes, and just in general. Number 10 will be conceptual. We'll go over these, and this is the last one. Okay, so 10 has 4 parts to it. So letter A, why does smoothness of a function affect decay rate of Fourier coefficients? So the reason for this, if we think about smoothness contra or versus Fourier decay, the more smoothness something has, it leads to the faster decay of the coefficients. So think about coefficients, right? They're going down as the smoothness goes up. So more smoothness leads to faster decay of the coefficients. Okay? So more of this, faster decay of that. Okay? Discontinuous at 1 over n, and then C1, 1 over n squared, okay, and then C to infinity, you're going to get exponential. Think in terms of exponential decay, okay? All right. So the fundamental concept there for why does smoothness of a function affect the decay rate? So this is what happens, and more smoothness leads to faster decay of the coefficients. So it's just to think about that C, what happens as it grows. And if you look at these, if you plot these, you can see what happens in terms of the coefficients. Okay. All right. Part B, when does a Fourier series converge uniformly? So again, this is from notes, textbooks, stuff that, sometimes professors put this stuff on to make sure if you're studying the intricacies of this. Uniform convergence occurs when these things happen. The function is continuous, piecewise smooth, and the periodic extension is continuous. Okay, that's when it converges uniformly. For part C, what is the physical meaning of the Fourier transform in signal processing? Well, physical meaning of the Fourier transform, it decomposes a signal into frequencies. It shows the amplitude of each frequency, and it's not only used in signal processing, it's used in a lot of other things, including heat flow, and you'll see this also in quantum mechanics too. So it has a plethora of applications. And for part D, why are boundary conditions critical in PDE, partial differential equation solutions using Fourier methods? So we could say here boundary conditions matter because they determine are eigenvalues and eigenfunctions, and from there eigenfunctions. And what they do is they ensure uniqueness and define the correct Fourier basis, whether it be a sine basis or a cosine basis. So that takes care of number 10, and believe it or not, that's all of them. Again, I went through this rather quickly. So, thanks for tuning in, and hope this helps a little bit, or hopefully a lot, or hopefully it helped. Pique some interest in Fourier analysis, and hopefully it helps provide some exercises to get ready for any exam or to review. All right, everyone, thank you very much, and have a great day.